Welcome to the DEFCAM. Under the direction of Air Headquarters, the Pakistan Air Force is executing a high-priority initiative to transition the JF-17 Thunder from a cost-effective multirole fighter into a sovereign, no-compromise combat platform. This transformation is not limited to airframe enhancements or engine upgrades, but rather, it centers on full-spectrum control of the aircraft's electronic systems. The focus is on gaining command of the entire electronic stack: radar, electronic warfare, mission avionics, and potentially electro-optical subsystems to engineer a tightly integrated software-defined combat suite that is fully domestically governed. This effort is being carried forward under the Operational Capability Upgrade and the PFX-Alpha development track, which together represent a comprehensive drive toward technological sovereignty in fifth-generation combat capabilities without relying on foreign vendors for critical functions. The central tenet of this undertaking is to shift from being a system integrator to becoming a system definer. In previous iterations of the JF-17, particularly in Blocks 1 through 3, the electronic systems were primarily assembled through international partnerships. Subsystems such as radar and electronic warfare pods were sourced as turnkey black box solutions with limited flexibility, minimal local configurability, and virtually no access to the underlying firmware or signal logic. This approach imposed constraints on how deeply the Pakistan Air Force could customize or evolve the aircraft's tactical behavior in response to changing threats, especially in complex electromagnetic environments. The PFX-Alpha effort aims to invert this paradigm. Instead of assembling prepackaged solutions, the Air Force is now working toward writing its own operational parameters, compiling its own firmware, and defining its own software signal flows from pulse-level radar emissions to cross-sensor situational awareness fusion. A key component of this transformation is the design and implementation of a new radar system. While the existing Block 3 variant incorporates an active electronically scanned array system jointly developed with a foreign partner, this radar still maintains proprietary control layers that restrict software-level access. Under PFX-Alpha, the radar architecture is being reimagined as a fully indigenous, software-defined sensor. The core objective is to build a radar that not only matches high-end peer systems in range, resolution, and agility, but one that is also fully defined, manipulated, and evolved through domestic software engineering. The effort entails designing custom radar signal processing chains, starting from baseband waveform generation to high-level tracking and clutter rejection algorithms. This includes the definition of pulse compression techniques, frequency modulation patterns, phase coding schemes, beam steering logic, and Doppler filtering functions, all of which will be authored within the mission computing environment and validated using domestically managed simulation infrastructure. The physical layer of the radar will be based on gallium nitride-based transmit and receive modules, selected for their superior thermal stability and power density. These modules will allow for greater peak and average power levels, enhancing the radar's range performance and target detection fidelity. Digital beamforming will be implemented as a baseline feature, permitting the radar to switch between multiple operational modes such as high-resolution synthetic aperture imaging, long-range target search, and low probability of intercept scans without requiring any physical reconfiguration of antenna elements. Additionally, the radar will be designed with shared aperture capability, enabling the same antenna array to be utilized by both radar and electronic warfare systems. This allows simultaneous search, track, and jamming operations to be conducted through coordinated time and frequency multiplexing within a unified hardware interface. Unlike conventional radar systems, which rely on fixed firmware libraries provided by the hardware vendor, the PFX-Alpha radar stack will be constructed around a modular firmware ecosystem. This ecosystem will enable national control over pulse repetition frequencies, beam dwell schedules, skin geometries, antenna gimbal strategies, and fast beam agility features required for modern electronic countermeasures. Local software developers will maintain full control over the waveform libraries, allowing new waveforms to be written and tested without foreign oversight or export controls. Equally critical is the radar's interface with the mission computer, which will be abstracted using custom communication layers that allow plug-and-play mode fusion with electronic warfare systems, targeting sensors, and real-time mission logic. This approach will allow the radar to participate in wider cross-platform data fusion efforts, including time-critical kill chains and cooperative targeting with network platforms. Electronic warfare represents the most contested and rapidly evolving domain of modern aerial operations, and the PFX-Alpha track places equal, if not greater emphasis on reclaiming control of this domain. In previous configurations, electronic support and electronic attack capabilities were fielded as modular pods developed externally and integrated onto the JF-17 as bolt-on components. These systems often included limited configurability and little access to core signal manipulation features. Under the new approach, the electronic warfare suite will be developed as an intrinsic part of the airframe's mission system. The goal is to construct a modular, wideband, software-defined electronic warfare architecture capable of both reactive and preemptive operations in dense electromagnetic threat environments. This architecture will be based on fully programmable radio frequency front ends, incorporating wideband digitizers, high dynamic range receivers, and low latency exciters. Digital radio frequency memory modules will enable deception techniques that replicate hostile radar signals in real time, creating false targets, ghost returns, and velocity gate pull-offs. Core electronic support functions such as threat detection, signal classification, direction finding, and threat behavior prediction will be handled by a parallel chain of embedded processors running low-latency, digital signal processing routines. These routines will be updated using a sovereign threat library populated with emitter characteristics, radar pulse patterns, modulation signatures, and behavioral templates of both regional and strategic adversaries. The threat library will be locally authored and continuously updated using signals intelligence captured during exercises, patrols, and operational sorties, ensuring that it reflects real-world threats rather than sanitized datasets from foreign partners. The electronic warfare system will also be fully integrated with the radar and mission computing core. It will not operate as an isolated system, but as an intelligent node within a broader mission architecture. Sensor fusion algorithms will correlate radar data with passive detection streams, such as time difference of arrival and angle of arrival estimates, to enable high-confidence emitter geolocation. Once detected, emitters can be automatically prioritized, categorized, and, if necessary, jammed or deceived through closed-loop response chains. Cognitive electronic warfare techniques are being explored to permit on-the-fly adaptation of jamming waveforms based on real-time threat behavior, using machine learning inference engines embedded in the mission computer. The aim is to create a system that can autonomously learn from threat encounters, adjust its behavior, and apply context-aware countermeasures without pilot input. At the center of the aircraft's adaptability is its mission computing environment. This subsystem serves as the digital nervous system that binds together radar, electronic warfare, electro-optical sensors, navigation inputs, data links, and cockpit interfaces. The legacy architecture was largely federated, with each subsystem maintaining its own processing core, data protocol, and software logic. PFX-Alpha shifts this model toward a tightly integrated, modular design, built on high-performance system-on-chip processors with dedicated digital signal processing and graphics acceleration units. The software stack will be layered, with a deterministic real-time operating system providing baseline scheduling guarantees and a middleware abstraction layer handling sensor communications, task management, and data routing. Unlike legacy systems that relied on proprietary operating systems supplied by foreign contractors, the new mission computer will run a fully POSIX-compliant, real-time kernel that is either custom-built or adapted from hardened open-source variants. This shift enables the development of high-assurance mission software routines under national control, including memory-safe flight logic, deterministic inter-process communication channels, and fault-tolerant watchdog services. More importantly, it allows the Air Force to update, patch, and reconfigure mission functionality independently of foreign vendors. Whether a new radar mode needs to be introduced, a threat classification algorithm must be updated, or a cockpit display format requires reconfiguration, these changes can be deployed internally through secure software channels, tested in local simulation loops, and fielded without requiring export approvals or recertification by external authorities. The sensor interface architecture will be abstracted to allow plug-and-play integration of future capabilities. Instead of binding mission applications directly to physical sensors, developers will interact with sensor data through standardized data layers that allow new payloads such as targeting pods, infrared search and track systems, or high-speed data link transceivers to be integrated via software adaptation alone. This decoupling also facilitates rapid prototyping, operational fielding of experimental systems, and midlife upgrades without hardware overhaul. The goal is to ensure that the aircraft's capability set is defined by software and computation, not hardware limitations or foreign design boundaries. The electro-optical systems, while not yet as centrally featured as radar or electronic warfare in the JF-17 configuration, are being actively explored for tighter integration into the mission system. These systems include imaging infrared sensors, laser targeting devices, and passive optical trackers. Under PFX-Alpha, the objective is to develop local control of the sensor's imaging pipeline, including noise reduction algorithms, dynamic range balancing, real-time optical recognition routines, and boresight stabilization. Electro-optical inputs will be fused with radar and electronic warfare outputs to build a unified, real-time threat and target picture. This enables features such as automatic sensor queuing, precision tracking, and target behavior analysis based on thermal and visual signatures. In summary, the operational capability upgrade and PFX-Alpha together represent a doctrinal leap in how the Pakistan Air Force defines, builds, and deploys combat capabilities. Instead of relying on modular imports, the service is investing in foundational technologies, signal processing algorithms, firmware logic chains, sensor interface protocols, and mission computing environments that are developed and validated in-house. The vision is to treat software as the gravitational center of combat capability, an asset that can be evolved, secured, and optimized without foreign constraint. Through this approach, the JF-17 Thunder is being reshaped into a combat aircraft that reflects the exact operational doctrine, threat landscape, and strategic vision of Air Headquarters, a sovereign system, built to adapt and designed without compromise. The development of the JF-17 under the operational capability upgrade in PFX-Alpha is increasingly dependent on how the aircraft's software-defined architecture can adapt to a rapidly evolving battle space. One of the core enablers of this transformation is the construction of a continuous software lifecycle pipeline within the Pakistan Air Force that mirrors high-assurance aerospace development standards while allowing for agile iteration. Historically, avionics and mission software were tightly coupled with proprietary hardware, requiring lengthy validation and certification cycles for even minor updates. Under the PFX-Alpha model, the design moves toward modular certification layers, where core services are validated once, and application-level logic can be updated through structured processes without affecting the integrity of flight-critical systems. This structure depends on a clear separation of safety-critical and mission-adaptive software domains within the mission computer, with inter-process isolation and determinism maintained through partitioned kernel execution and memory protection units. In this framework, mission software is developed in discrete logic blocks. Each block corresponds to a specific capability set such as radar beam scheduling, emitter classification, or track correlation and is compiled and tested independently. These modules are versioned, sandboxed, and loaded through a secure boot process that ensures integrity while allowing continuous evolution. This is supported by a full-cycle development and test ecosystem built around hardware-in-the-loop simulations, synthetic sensor emulation, and virtualized twin environments that mirror actual aircraft behavior down to sensor latency and processing delay levels. These digital twin environments are calibrated against real flight data and serve as the proving ground for every mission capability before it enters operational use. Once deployed, the same infrastructure is used to replay sortie logs, capture system telemetry, and trace logic decisions for post-mission evaluation and optimization. The goal is to achieve a feedback-driven development process that incrementally enhances capability based on real-world usage data without requiring any involvement from foreign stakeholders. A significant focus area is the extension of mission computing architecture into electromagnetic spectrum management. With increasingly congested signal environments and the prevalence of networked warfare, the JF-17 under PFX-Alpha is being equipped to operate as an intelligent node in a contested information battle space. This includes active participation in electromagnetic order of battle generation, real-time emitter geolocation, and coordinated spectrum maneuvering. To achieve this, the mission computer must process, prioritize, and deconflict multiple overlapping streams of spectrum activity across radar, electronic warfare, communications, and data link operations. The software stack includes a dynamic spectrum controller that assigns frequency usage, pulse scheduling, and antenna resource allocation based on mission priorities, tactical constraints, and detected threats. These allocations are updated in real time using a decision-making framework that considers factors such as jamming probability, emission visibility, and platform survivability. The data link architecture of the JF-17 is also being refactored under PFX-Alpha to support sovereign control, advanced routing protocols, and seamless mission collaboration. Traditional data links in earlier JF-17 variants were limited to fixed waveform standards and externally developed communication stacks. The future architecture will rely on a modular data link core that supports software-defined radios capable of multiband, multi-waveform operations with embedded link layer encryption and adaptive modulation. The link layer will implement time-synchronized, low-latency protocols optimized for combat air operations, including air-to-air and air-to-ground cooperative targeting, dynamic threat sharing, and precision queuing of networked sensors. These systems are being designed to interoperate with both legacy command and control networks and future indigenous combat cloud concepts. Critical to this capability is the ability to conduct autonomous link negotiation, signal anti-jam strategies, and dynamic frequency hopping to resist electronic attack while maintaining mission synchronization. In parallel, the aircraft's signal intelligence functionality is being deeply integrated into the mission system, moving away from standalone recorders or passive receivers. Under PFX-Alpha, the aircraft will be capable of operating as a tactical signal intelligence collection platform, recording and analyzing emitter behavior in real time. This capability enables not just emitter warning but adaptive signal exploitation. Detected waveforms can be decomposed into pulse structure, modulation type, sweep pattern, and intrapulse features, enabling the aircraft to build emitter fingerprints in flight. These fingerprints feed into both the electronic warfare countermeasure engine and the National Threat Library database. The Threat Library Management System includes an embedded learning loop where new emitters encountered in the field are captured, processed, and inserted into the operational library in near real time. The same infrastructure allows for countermeasure effectiveness to be evaluated post-mission using captured radar return patterns and response logs. Another critical innovation is the emergence of cognitive systems within the aircraft's electronic stack. These are machine learning-based agents embedded within the mission computer, trained to detect patterns, classify behavior, and recommend actions based on real-time operational context. In the radar system, cognitive agents analyze return signals for anomalies, track maneuver patterns, and classify targets not just by kinematics but by observed radar cross-section profiles and behavioral heuristics. In the electronic warfare system, cognitive modules analyze the threat landscape, detect adversary countermeasures, and adjust jamming strategies accordingly. These agents operate within a bounded decision space, supervised by human operators during training and hard-coded to fall back to deterministic modes under ambiguity. Their objective is not to replace the pilot or mission commander, but to provide decision support in compressed timeframes where manual response would be too slow or suboptimal. The use of machine learning also extends to maintenance and diagnostics. The aircraft's onboard health monitoring system collects telemetry from all major subsystems, including radar modules, power amplifiers, mission processors, cooling systems, and sensor packages. These streams are processed using predictive maintenance algorithms that detect deviations from normal performance envelopes, flag early warning indicators, and recommend preemptive inspections or part replacements. This reduces unplanned downtime and optimizes fleet readiness. Combined with cloud-based ground stations and secure data ingestion pipelines, mission logs are automatically analyzed at squadron level for trends, bottlenecks, and hidden faults. Feedback from these analyses feeds back into both the software update cycle and hardware design roadmap, creating a closed-loop optimization architecture. PFX-Alpha also introduces a shift in cockpit interaction philosophy. In prior generations, pilot interaction with mission systems was largely procedural, with the pilot required to manage multiple sensors, interpret raw data feeds, and make complex tactical decisions under high workload. The new interface model focuses on cognitive ergonomics, situational awareness fusion, and task automation. The cockpit displays will present unified threat and target views derived from sensor fusion engines that correlate radar tracks, optical cues, electronic signatures, and mission intelligence overlays. Instead of switching between modes and sensor pages, pilots will receive prioritized tactical suggestions, threat classification overlays, and action prompts filtered by mission context and rules of engagement. These overlays will be informed by real-time sensor performance estimates, line-of-sight availability, platform maneuver history, and cooperative network data. The display generation engine is built around a modular graphics pipeline with GPU acceleration, allowing it to render dynamic visualizations such as synthetic aperture radar images, three-dimensional threat corridors, terrain occlusion maps, and mission timelines. This allows the pilot to not only see threats and targets, but to understand them in context, when they were detected, how they have moved, and what options are available to respond. Automation features allow for pre-authorized countermeasure responses, sensor reallocation based on threat direction, and queuing of weapons to verified targets without manual designation. This reduces pilot cognitive burden in high-speed, multi-domain engagements and increases survivability in contested environments where reaction time is a critical determinant. The emphasis on electronic sovereignty also extends to the sensor fusion core. Rather than relying on pre-packaged fusion engines, PFX-Alpha will feature a locally authored fusion kernel built around track-level and detection-level correlation engines. These engines ingest data from radar beams, electronic support measures, infrared search tracks, optical cameras, and mission data links, using probabilistic association algorithms to merge them into a single situational model. This model is continuously updated using Bayesian filters, Kalman smoothers, and motion prediction heuristics that account for emitter mobility, target acceleration, sensor uncertainty, and line-of-sight occlusion. When contradictory data appears, for example, when radar and infrared sensors disagree on target identity, the fusion core applies conflict resolution logic that weighs sensor reliability, detection geometry, and historical behavior to infer the most likely interpretation. This level of fusion is essential not only for pilot awareness, but for enabling artificial intelligence modules to make informed tactical decisions. The plug-and-play design philosophy of PFX-Alpha will be critical in future-proofing the platform against obsolescence. Every sensor, processor, and communication unit is being designed with standard physical connectors, abstracted communication protocols, and software adaptation layers that decouple hardware presence from functional integration. This means a new targeting pod, for instance, does not require mission software recompilation but only a driver interface definition that maps its outputs into the fusion engine. This modularity also applies to software itself. Capabilities can be packaged as microservices, deployed as containers, and scheduled by the mission operating system based on processing availability and mission relevance. In combat, this allows the system to prioritize what software runs. Radar imaging can be deprioritized for electronic warfare when under heavy attack, or threat libraries can be loaded dynamically based on theater of operation. This adaptability extends the aircraft's usefulness into multi-mission roles with minimum software overhead. The Air Headquarters has also initiated internal research programs into next-generation sensor technologies that will feed into later iterations of PFX-Alpha or into entirely new platforms. These include dual-mode radar systems that operate in both microwave and millimeter wave bands, conformal array antennas integrated into the airframe skin, distributed aperture systems for spherical situational awareness, and quantum-resistant secure communication channels. While some of these technologies are still in prototype phases, the modularity and software-centric foundation being built now ensures that they can be integrated rapidly when mature. The emphasis is not on reaching a final product state, but on building a digital infrastructure that evolves continuously, where every new line of code, waveform definition, or signal behavior improves the platform iteratively. This transformation demands a parallel evolution in human capital. The Pakistan Air Force has ramped up its investment in embedded systems engineering, signal processing, operating system design, and cyber-physical system validation. New cadres of systems engineers, mission software developers, and electromagnetic spectrum specialists are being cultivated through dedicated training programs, university partnerships, and operational fellowships. The aim is to create a domestic defense software industry that is not just capable of supporting existing systems but of leading innovation in military electronics, artificial intelligence integration, and software-defined sensor architectures. The long-term vision is not just to modernize the JF-17, but to create an indigenous design language for future combat systems, a language written in source code, signal patterns, and compiled firmware. Thanks for staying for so long. Stay tuned for upcoming videos.